Hello everybody. Today I'm playing with this piece of junk, which is of course not a piece of junk, it's a fine machine. It just have seen some better days. I think it's fallen down maybe once or twice because there are buttons missing. There's the power button missing, but besides of some cosmetic problems, it works pretty well. It's a Colin Duxeo BX-10 patient monitoring system. Let's see at the label. It says patient monitor BX-10 MA from Colin Corporation in Japan. Manufactured 2007. It's not the newest product, but it's fun to play with. So let's switch it on and we will see what it can do. Power button. There is a fan inside, you can probably hear that. Alarm test, display test, and there we go. So I hope you can see the display here. So let's go back. So what is it good for? First of all, these displays here on the left side tell you a lot about the blood pressure. There is a connector here for a hose for this cuff that is wrapped around the arm, which is pumped up. You certainly know that from blood pressure measurement. There is a pump inside that provides the air pressure for that. And here you have a display for the systolic pressure. That's the pressure when the heart muscle contracts and shoots the blood through your veins. This one is the diastolic pressure. That's the pressure, the lower value that you measure when the blood gets back into the heart, when the heart expands and fills with blood. And MAP is the mean, I don't know what A stands for at the moment, the mean pressure between the systolic and the diastolic. You get a curve like that, and the mean pressure is, it's like in AC electric, mean voltage, peak voltage, lower peak, something like that. On the right side we have SPO2, that means it's the saturation of oxygen in the blood. So an optimal value is 99 or 100%. Then your blood is completely saturated with oxygen. The P here stands for pulse oxy measurement. I hope I pronounced that correctly. It basically means you get a sensor like this, where you stick your finger in, and then it shoots some different wavelengths of red light through your finger. And from the absorption of certain wavelengths, you can determine how much oxygen is in your blood. So blood that is saturated with oxygen is bright red, and if it's not saturated, if if it's used its oxygen, it gets darker. So you actually measure the color of your blood, and then you can calculate the percentage. PR here is pulse rate, so you can see how fast the heart of the patient is actually going. Now let's connect that and I'll show you how that works. I have to switch it off because I found that it doesn't recognize the sensor here while it's powered on. It's not a hot swap thing. Okay, power it on again. Maybe if I switch the light off a bit. Ah yeah, here you can see the red LED. You can probably see different colors, different wavelengths, different intensities. So the unit tries to find a finger. Oh, we actually had a reading there, which is of course wrong. And then on the other side of the clip there is a little square sensor array. Now it beeps because something is wrong with the sensor, so I put my finger in. Light goes through my finger. It doesn't hurt really. Oh, it doesn't hurt at all. So now we have a reading 91%. 95, yes, that's better. Everything below 90 would be probably a problem. So everything above 90 is more or less okay. 99 would be fine. Oh, that rhymes, okay. 97, okay, that's something nice. It depends how much you breathe, how intense you breathe. So if I hold my breath, for example, it will probably drop. My pulse rate is 90 at the moment. Seems that making videos for YouTube makes me a little bit nervous. But I'm not really nervous. Let's try it. I hold my breath and we will see how low we can go. Okay, that's enough. Whew. So you have seen my heart rate, my pulse rate has risen up. It's over 100, so the heart tries to compensate that low oxygen level by pumping harder. My oxygen level has dropped to 91 now. So it all has a delay because the blood has to circulate. So now it goes up again. 98, 97, okay, that's fine. I feel better, yes, thank you. I'm measuring here on my finger, so when I hold my breath the blood with a low oxygen level first have to travel through my arm, through my finger, back to them. And that takes a while. That you have seen, it took a couple of seconds before it dropped, and then after I restarted my breath, it also took a couple of seconds to go back to normal. Okay, pulse rate is coming down a bit. Okay, everything is normalizing. Now, on the LCD display here, you see my pulse. The pulse is of course also measured here with this clip. You can see the pulse by well, it's waves of blood that pass this sensor, so it can determine. It's not exactly the same as you have on an electrocardiogram, but the curves are similar. Here you see the systolic pressure. We have no value here. We have the pulse rate. It's the green arrow here, which is at the moment 92. And the white band is the range where pulse rate is okay, and everything above or below would trigger an alarm. So this pink band here is the alarm level. The oxygen saturation alarm level is 90%, so if I go below that value, an alarm will sound. Maybe I can trigger that by opening this clamp. I'm not sure. I can't not take my finger completely out because that would, well, that's what happens now. It cannot measure anymore. That gives a yellow alert, and if we go below the alert level here, we get a red alert, which tells the nurse that something bad is happening. Well, I'm sorry you couldn't see that. I take my finger out. Takes a while. Yellow alert. You can stop that. And as soon as I put my finger back in, the alert will go off. Okay. Now that's about what it does. Here is the symbol for the blood pressure measurement. If I press this, it's now on aus, that means off. So we don't do any measurement because I don't have the equipment to do that. We can select here the time in minutes. So for example, we want to make a blood pressure measurement every 15 minutes. So I set that. You can see it here, cycle 15 minutes. 1 minute. I could measure the blood pressure every minute, but I think patients won't like that because, well, it's always this pumping of this cuff around your arm. So I set it off. I can also push this button to manually. You hear the pump is running, but there is nothing attached to pump up, so after a few seconds now we get the red alert. Something is horribly wrong, of course. It is also possible that the patient has moved in the bed and ripped away some hoses or some wires. Okay, what can we do else? There is a menu select button. We have different screens. For example, here is a list of the measurements. They are from yesterday. No, maybe from today. So I have every minute here. I set it like that. You can choose. Let me see. It's on that screen. Here you can say every minute, or every 2 minutes, half a minute. So that's the shortest interval to log the data, so 30 seconds. And the longest interval is 2 hours. So if you have, for example, you have to monitor a patient for a very long time, you can set it to 1 hour, so it takes one measurement every hour, or every minute, as I like it here. There is also the speed of, I don't know, you can attach a print, maybe it's for that. Then you have the date, the time, can set the time and date, which is important if you have locked data. In this menu here with the speaker symbol, you can set the alarm volume, the control tone. You can set how the sound sounds, so you can have a high, a medium and a low frequency alarm. So for example, if you have more than 1 units in one room, you can say one patient has a high alarm sound or something like that. Okay, exit. Then we have this is the display menu. We can choose what we want on the main display, which is this here. We have the waveform, we have the alarm levels. So we can hear that's waveform, alarms. We can also have a graphics display, but that is only possible if we switch off the waveform, so you cannot have both of them. You can switch the LCD off, maybe in the night it will disturb people while sleeping. You can set the clock on or off if it displays the clock. Intensity, no brightness of the display. Exit. That's blood pressure measurement. I'm not sure, I'm not a doctor, there are some values that are interesting if you know what you do. And that's the alarm level setting. For example, I can choose the lower, you can see the cursor here, probably. Okay, I think that's better. You can go to the menu here, set the low, you push the button and then you change that. And you also see the red or the pink bar here gets longer or shorter. So I'm now at 94, that's the blue dot here. So if I set the alarm to 98, which is higher, so I'm below that alarm level now. Set, exit. Yeah, I already have a yellow alert. Oh, now I have a red alert. and you see the value that is out of the limit blinks, so 95 is too low because I set my alarm to 98. Okay, let's go back. So 90 was okay. Exit. Okay, let's see what happens. It's still 95, so I think I have to silence that alarm here. Okay, maybe again. I haven't found a user guide, so I'm just trying, and I think it's rather nice to work with because everything is a bit logical. Everything is written clearly what it is and what it does, and well, there are only a few things that you have to know. For example, if you go to the to the listing, which is here, you can erase all that stored data. So you also see there is an error here. You also see error entries if there is something wrong with the measurement. So to erase this, I push the button and hold it for a couple of beeps, and then it makes ding and everything is empty. Okay, and of course the same works for the blood pressure part. So you can monitor a patient if his blood pressure and oxygen saturation is okay. Now let's have a look inside. Unplug the mains. A funny detail, there is the mains plug and it has no earth connection, which I think is a little bit strange because all this medical equipment have very good earth connections because there is a patient directly connected to it. Maybe it's not necessary because all the sensors here are insulated. There is not a direct electric contact to the patient, but well, I don't know. Maybe it's just broken off. Maybe it's one of the problems. So let me change my camera view. Okay, here I am again. It has a lot of screws. It is built quite solidly. Well, it must, because people in a hospital are not always take care about their equipment, because patients have priority, which is absolutely right. So these things must be built quite well under these rough conditions. So I put in some screws here that are not original. I have already opened it before, I admit it. A lot of screws here on the bottom. It's about 2 screws for every side panel or front or back panel. maybe even 3. So the longer screws here are going into the power supply, which is on the bottom of the device. Okay. So I think, no, there's another one. Okay, so there is another one. There is a connector here. I don't know what is it good for. I think you can replace this handle with something else. Maybe that's the space where the printer goes. You can have the printer for that. There is also space with some empty not connected cables. Maybe another interface, maybe a network card or something, I don't know. Haven't found any information. Here is another connector. It's for a battery pack that goes on the bottom of the unit. You can have a battery pack, so if you have to move a patient from one station to another, or maybe in an ambulance car. Okay, back comes off. So you also see there's a lot of broken plastic here. So that's the side panel. There is a hose that comes from the pump unit, which is this one here, to the outlet port, or better, yes, it's air pressure, it's an outlet. Oops, the other side just fell off. You also have a label that's left. The other one has a right. Okay, what do we have here? We have a CF card slot, or a, yeah, is it a CF? Yeah, it could be. So you can put the CF card in, which goes through that slot here, which is protected by a rubber cover like this. So probably you can store your data on this CF card and have it together with your patient, or if you change the unit because battery goes low or whatever, you can change the CF card and continue your measurement. So there is the cable that is not connected. Now it's both sides not connected. So how is it going? There's something loose here. Okay, well, that's probably not the way to do, but okay, it's broken now. Alarm button made of rubber. Everything must be more or less watertight, or at least immune against all these fluids that are used to clean everything, alcohol, disinfectants. So that's the hose with a angle inside. It comes out here from the pump unit. So there's a flat ribbon cable going into that pump. So how to remove this? I think I have to take away the entire metal frame here. There's another screw. It's already unscrewed. Okay. Ah, there is a screw underneath that flat flex cable. Yes. some more connections and more connections. That's probably the connector from the power supply. There's a black wire, just one single wire. Okay. These cables are soldered. Oh, it's a little bit complicated inside. More screws. Japanese people love screws. I used to work with Sony equipment, especially the old TVs, and you always had a ton of screws on everything. And European manufacturer. So, okay. Oh, it's a little bit black here, but I don't think that's because of heat. I think that's the motor that drives the pump. That's the pump housing, maybe a reduction gear, and I think that's simply some oil or grease that leaks out here. Ah no, it's the rubber. It's something you sometimes see in older equipment, that black rubber gives a little bit away of its blackness, so it makes everything black that is around it. Sometimes, maybe it's also a little bit of air leaking out here, I don't know. There is a metal shield which is not screwed nowhere, but somehow it's sticking. So you can see here, well, I hope you can, move the light a little bit. There is an air pressure sensor here and another one here, connected with a silicone hose that comes from this sort of manifold here, maybe a filter or something like that. So I just want to remove that metal part. I don't get it. Maybe I have to be a little bit rough. Ah, that's a temperature sensor here. You can see a little black knob here. Temperature sensor. Because if you want to measure air pressure precisely, you have to know the temperature, because air pressure changes when it's hot or cold. And in this case, there is a catch. It's so easy when you know how. So, what do we have here? There are two little, it looks like a relay, but it's in fact an electromagnetic valve. Okay, it comes out. Wow, it has more electronics inside than I expected. I thought all the electronics is in the main box here. So, what do we have? At Mega. What number? I need my magnifier glass. At Mega 163L 4AC 0234. That's maybe the production date. It's a little bit early because the unit is 2007, so 2002. I had it relatively long on stock, if that's true. So you can figure out yourself what's going on here. There's certainly some programming. What do we have? A Maxim chip here. Max 394CWP. I think that's some sort of serial interface. because Maxim is very good in these things. So now you can see the pressure sensors, the two. That's the manifold that connected here. So we have a pump, a small pump with the inlet and the outlet. Which is which? Don't know. Have to switch it on. A rolling pump. Yeah, rolling pump. Interesting. We will see what a rolling pump is. So I disconnect it here. Then we have the manifold. So if I remember right, yeah, okay, that's where the pump is connected. This is probably the intake, goes to an air filter. That's the output of the pump, probably, I think. Going to the two pressure sensors. Going to two identical valves. And now you can see there is the coil, electromagnet. There is a plate that is how do you call that? The magnet attracts that, so I just ripped away the cover, so it does this motion here, like a relay, but instead of switching an electric connector and an electric switch, it probably closes the hole here with this rubber with this small rubber plate. Let me see if we can take that out. Not that easy. So you just have to trust me that I think it closes when it's energized and opens, so all the air will escape here to, well, and the pump pumps air in. So the pump pumps air in, and this one here opens to release the pressure, because you have to release the pressure after the measurement, or your patient will probably lose its arm because the blood is not circulating anymore. This is more or less an air filter. This is an air relay, or a mechanical valve. So that's the other side of the board. Sensors, some capacitors, some inductance, L1, some sort of coil. Yes. Oh, optocouplers, I think. Yeah, looks like it. So let's have a look at the pump before we go to the rest of that. Let's open that up. I just need a smaller screwdriver. That's this one. And now the charge sounds its bell, so I stop this for a moment. Okay, let's see what this rolling pump is doing and how it works. I forgot to switch on my microphones when I recorded this video, so I have to do a voiceover here, so that's the reason why it sounds a little bit different. Silly me. The pump is running on 12 volts about, and you can, or you could hear, if I switched on my microphones in the right moment, that the air comes out in the center. You can hear the air blowing out, and this is the intake port. When I block it, the pump starts to sound differently. So on the top plate, oh no, here you can see the pistons. If you move one down, the others come up in a circular motion. These are the intake valves. There are little rubber plates, very thin rubber sheets. And the air comes in, it goes underneath all the 4 valves, and the air pressure lifts up this rubber sheet and finds a way into the cylinder. You can see it's very thin rubber. Then in the cylinder the air gets compressed, and the only way out is through the center. There are 4 tiny rubber flaps, one for each cylinder. They block the way out, so the way out is these 2 grooves here for each cylinder, and the rubber flaps are inside and block these grooves one way, and when the air wants to get out, these flaps move out of the way, open the grooves, and the air can pass through. Now let's see how this all comes together. There is the motor. On the motor is a little wheel with a pin. The pin is in an angle, it's not 90 degrees. And this is in fact a crankshaft. A crankshaft that connects to the center piece here, that moves the pistons around. And that's why it's called a rolling pump, because, well, it rolls the pistons around somehow. So let's assemble that again. I want to keep that pump. So let's have a look at the rest of the unit. We see the main board, power supply, 2 flat ribbon cables go to a smaller board, which is directly underneath the pump module and well between the power supply and the pump module. I have no idea what it could be. Here's the power supply, little fan, shielding. That's the other board where the 2 flat cables go. This is just a connection board, small connectors on one side, bigger connectors on the other side. And there is a board with a big chip. Looks like a CPU or something. A lot of stuff. I didn't expect that in this position. That part looks a little bit like a RAM or maybe a flash memory, maybe with some firmware on it, or even possibly a storage for the logger data. Let's peel off the sticker and have a look what chip is underneath that. It's an Analog Devices DSP 21061L ADSP. A little bit surprising to find it in this position. I would expect that to be on the main board, but they certainly have their reasons. Maybe they simply didn't have the space to put it on the main board. A small Sanyo brushless fan. It's a good one, not of the cheap Chinese ones. And as I said, I forgot to switch on my microphones because the fan was a little bit noisy and perhaps it would need some new bearings or just replacing the fan. But I won't do that because that unit goes where it came from, to the scrap bin. That's the power switch and the power lead and the power cable, which has of course a little safety hook on the back side. Not on the front side where you can reach it, but on the back side where you need tools to get it away. Funny thing here is this is a two-board construction, the power supply. On the lower board there's certainly some battery charger circuit, and there are only two wires coming from the upper board, so it seems that the mains power supply only provides 1 voltage with the red and the black wire, and all the rest is done on the second board. Now this is the second board. Looks like some DC-DC converters. This is the output connector with the red, black and one blue wire, this one here, that goes to the main board. And the smaller connector is the input that comes from the mains power supply. You have some interesting low profile capacitors here. So I think they had absolutely have to had it in a certain maximum height. So they choose this low profile components. From the look of it, it's about 3 DC-DC converters, or maybe 2 and the battery charger. So the plastic here has yellowed very much, so because the power supply has heated it up, and it's also quite an old unit, so the plastic here is very brittle, it breaks apart easily, which is good for disassembly, of course. There are 2 plastic screws on each side. So here we have the power supply, shielding all over it, and a very strange feature on the top. We will see that again, yes. There is a copper shielding and a thick wire screwed across it. I think this is to lower the resistance from one side to the other, because the copper is not very thick. But it is still a strange construction. I have never seen that before, that someone passes a wire across a copper shielding to make it conduct better or something like that. I don't know. Okay, that's the plastic base insulation, then again shielding and insulation all around the power supply. Insulation is a very important thing, because this is a medical device, and medical power supplies have they are regulated, they are constantly checked, they have to be safe in any way, because there is a human being directly connected to this unit, so you must avoid every danger to have any leakage currents from the mains to the low voltage side. So you see the insulation gap is very wide. They even removed the green painting. and there are also insulation slots milled into the board. Well, you can see here there's a lot of input filtering, and it's a two-stage power supply. It's a multi-input. It's from 100 to 240 volts input. There are also insulation gaps on this controller circuit board. There is the power supply chip on the underneath the heatsink there. There is the input with no earth connection. Filter coils, common mode filter coils. This is a spark gap inside a heat shrink tube to prevent any lightning flashes. Some capacitors there on the side, a MOF to suppress overvoltage, rectifier here. A lot of filter capacitors before and after those yokes. In big input capacitor, 450 volt rated. Then the output switching transistor with the transformer next to it, and some output capacitors. Because we are only supplying one voltage, it's relatively simple. The the input capacitor is always charged to the same, about 400 volts. So there is a primary switcher, which is in fact a boost converter. So if you only have 100 volt input, it boosts that voltage up to 400 volt DC to charge the input capacitor, and if you have 240 volts, it doesn't have to boost a lot, and it goes more or less directly to the capacitor, keeping it at the same 400 volts. So let's have a look on the main board. This is where all the rest of the unit is located. I just cut away the cables to make the view free for everyone. So there is a big Hitachi chip, battery, the same battery as you use in your PC mainboard, 2032, 3 volt backup battery. Then there is also an SD card slot, a super cap, a small super cap. It's 0.2 farad. a big Hitachi chip. You can, if you want, go and search for the datasheet. It's certainly some sort of microcontroller. There's something that looks like a RAM and a flash storage chip. Maybe for the firmware, maybe for the data that is collected. Then here is the connector for the SPO2 sensor. That was that finger clip thing. And you can see here it's completely insulated from the rest of the unit. The power for the electronics goes to that transformer, is then rectified and regulated in a small power supply, and here are some optocouplers for all the signals that go in and out. This is the pin where the shielding cable from the power supply was connected. This is the power supply part of this I/O module. Then we have another module. I don't know what this plug is for. Maybe it has to do with the blood pressure measurement, or it is some sort of network interface which has the same insulated circuit with optocouplers, with a power transformer, a small power supply on the module. There are also insulation gaps cut out to make it totally safe and to prevent that any dust could probably cause some leakage or dirt. That's the speaker for the alarm beeper thing. Flat cable goes to the display. On the back side we also see these insulation gaps and more optocouplers. This is the power transformer, which has also a cutout in the board. Insulation here, insulation around the other I/O port. And now let's have a look on the front panel board. There is some driver circuits, also the driver for the cold cathode fluorescent backlight, a high voltage fluorescent backlight. There is the inverter circuit, a high voltage cable that goes to the tube. Then the transformer that makes the high voltage and the driving circuit around it. There are two funny looking components. These are normal electrolytic capacitors, but they are mounted inside a rectangular plastic case. There are some driver chips. They look a little bit like stepper motor drivers, but there are no stepper motors inside. So my guess is these are the drivers for the LEDs. There are a lot of LED displays over there and they need a little bit of current, so they put in this heatsink pinned LED drivers. The board is a little bit sticky. There had some adhesive tapes around. So, and this is the display made by Sharp. It's a standard display you would find in all kind of consumer electronics or small industrial devices. This is the rotary encoder from the big knob. You can turn it, you can push it. These are the LED displays. These LEDs show the heart rate, the pumping action of your heart, your pulse. Okay, that's the word. Some buttons, reset buttons, alarm buttons, and this is the alarm LED PCB. I think they are half red and half of them are yellow LEDs, depending what kind of alarm it displays. Well, and that's about it. Thanks for watching.